Before today's AI revolution, there was a dream. In the 1940s, scientists began to wonder if thought itself could be turned into mathematics. By the 1950s, machines were proving theorems, solving puzzles, and convincing researchers that artificial intelligence was near. The future felt inevitable, a world where computers would think alongside humans. But intelligence was harder than anyone expected. Progress slowed, promises faded, and by 1973 the excitement collapsed into silence. This is the story of AI's first rise and its first winter. In the 1940s, long before AI had a name, the essential ingredients were quietly coming together. In 1943, neurophysiologist Warren McCulloch and mathematician Walter Pitts, inspired by the earlier mathematical biology work of Nicholas Reshevsky, published a paper that would later be seen as one of the hidden birth certificates of artificial intelligence. What they proposed sounds simple today, but at the time it was revolutionary. They imagined neurons not as mysterious biological structures, but as logical devices. Each neuron, in their model, behaved like an all-or-none switch. It either fired or it didn't. Inputs arrived, numbers were summed, and if a threshold was crossed, the neuron produced an output. The brilliance wasn't in a single neuron, it was in what happened when you connected many of them together. McCulloch and Pitts proved something astonishing. Networks built from these simple units could perform logical reasoning. They showed that combinations of neurons could reproduce operations like and, or, and not, the same building blocks used in digital circuits and formal logic. In other words, biological-inspired networks could compute. Until then, the brain was mostly discussed in biological or philosophical terms. McCulloch and Pitts reframed it as a system that could be understood mathematically. If neural activity could be represented as logic, then maybe thinking itself could be described and eventually engineered. The truly exciting implication was if these networks were arranged in the right way. They might not just calculate, they might learn. It was later proven by Donald Hebb in 1949. They built a bridge between neuroscience, mathematics, and computation. For the first time, someone had shown, with equations rather than speculation, that machines inspired by neural structures could, in principle, carry out reasoning. This work quietly influenced entire fields. It laid foundations for cybernetics, automata theory, cognitive science, and eventually modern neural networks. Decades later, researchers would look back and realize that many of the biggest ideas powering modern AGI started here, in a paper that tried to answer a deceptively simple question. What if thought itself could be expressed as logic? And once that question was asked, the race toward artificial intelligence had truly begun. In 1945, John von Neumann circulated the EDVAC first draft, a blueprint for the stored program computer where instructions and data live in the same memory. And in 1948, two intellectual pillars arrive. Claude Shannon formalizes information in bits, while Norbert Wiener frames feedback and control, how systems correct themselves in noise. AI began as a convergence: logic, learning, information, and control. The 1950s, the decade where optimism got organized. In 1950, mathematician Alan Turing published a groundbreaking paper called Computing Machinery and Intelligence. Instead of asking what thinking really means, he proposed a practical test. If a machine could hold a conversation so well that a person couldn't tell it apart from a human, it could be considered intelligent. This idea became known as the Turing test and transformed AI from philosophy into science. Turing also predicted that machines could learn through experience, much like children. His vision that still shapes AI today. In 1951, Marvin Minsky and Dean Edmonds built a machine called SNARC, the Stochastic Neural Analog Reinforcement Calculator. It wasn't software. It was a physical device made from hundreds of vacuum tubes, motors, and wires, roughly the size of a piano. It didn't look like a computer at all. SNARC contained about 40 artificial neurons connected together. Each connection had a strength, similar to how synapses work in a real brain. The goal wasn't to perform calculations like traditional computers of the time. The goal was to learn. To demonstrate this, the machine simulated a rat trying to find its way through a maze. At first, its choices were mostly random, but whenever it reached the correct path, the system received a reward. That reward slightly changed the connections inside the network, making successful choices more likely in the future. Over time, the machine improved, not because someone reprogrammed it, but because it adapted from experience. This was a revolutionary idea. Computers were supposed to follow fixed instructions. Snark suggested something different. Intelligence could emerge from many simple units learning together. In 1956, Dartmouth College hosted the famous summer research effort proposed by John McCarthy, Marvin Minsky, and colleagues, using a sentence that reads like a manifesto. Every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that a machine can be made to simulate it. In the same era, Alan Newell and Herbert A. Simon, working together with programmer Cliff Shaw, introduced a system called the Logic Theorist, a program that many historians consider the first true artificial intelligence system. Unlike earlier computers that only followed fixed numerical instructions, Logic Theorist was designed to imitate human reasoning. Its goal was ambitious: prove mathematical theorems using symbolic logic, the same kind of reasoning human mathematicians use. The team chose a famous challenge, Principia Mathematica, the monumental logic work by Alfred North Whitehead and Bertrand Russell. The program explored chains of logical steps, searching for valid proofs, not by brute force, but through heuristics, rules meant to guide it toward promising solutions similar to human problem-solving strategies. The results were astonishing. Logic Theorist successfully proved 38 of the first 52 theorems in the book, and in at least one case, it even discovered a shorter, more elegant proof than the human authors themselves had written. In 1957, Newell and Simon introduced the General Problem Solver, or GPS, a program designed to imitate human reasoning across many kinds of problems, not just one task. Instead of hard-coded answers, GPS worked by comparing a current situation to a desired goal and searching for steps to reduce the difference, a strategy called means-end analysis. It could solve logic puzzles, math problems, and symbolic tasks, showing that problem-solving itself might follow general rules. GPS wasn't truly general intelligence, but it introduced a powerful idea. Thinking could be modeled as a search through possible solutions. In the same year, AI pioneer Herbert Simon made one of the boldest predictions in technology history. Speaking about early AI systems, he declared that machines could already think, learn, and create, and that their abilities would grow rapidly. He predicted that within 10 years, a computer would become a world chess champion and prove important mathematical theorems. The confidence captured the spirit of early AI, a belief that human-level intelligence might be just around the corner. In 1958, computer scientist John McCarthy, one of the founders of artificial intelligence, introduced a new programming language called Lisp. Unlike traditional languages focused on numbers, Lisp was designed to manipulate symbols, making it perfect for AI research. Its flexible structure allowed programs to represent knowledge, reason about problems, and even modify themselves. For decades, Lisp became the main language of AI laboratories around the world. McCarthy believed intelligence could be described mathematically, and with Lisp, he gave researchers a tool to begin building that vision. In the 1960s, symbolic AI took off, systems built from rules, symbols, and formal structure, while the public imagination absorbed machine minds through fiction. In 1960, McCarthy's Lisp became a foundational language for symbolic AI, specializing in manipulating symbolic expressions as easily as numbers. In 1962, psychologist Frank Rosenblatt developed the perceptron, one of the first machine learning models inspired by the brain. Built in hardware and software, the perceptron could learn to recognize simple patterns by adjusting the strength of connections between artificial neurons. Instead of being programmed with fixed rules, it improved through training, changing its internal weights when it made mistakes. For many researchers, this felt like a glimpse of real machine intelligence. Newspapers even predicted machines that could see and think. But the excitement didn't last. Scientists soon discovered that single-layer perceptrons had serious limitations, setting the stage for both progress and the first AI winter. Optimism in artificial intelligence grew rapidly. Researchers built early systems that could solve algebra problems, prove logical statements, and understand limited human language. Funding increased as governments believed human-level AI might arrive within a generation, but cracks soon appeared. These programs worked only in controlled environments and struggled with real-world complexity. In 1966, a critical report on machine translation revealed how limited AI still was, leading to reduced funding and growing skepticism. The first wave of AI excitement was beginning to slow. AI faced its first serious reality check. Early optimism had promised rapid progress, but researchers began running into hard limits. Systems that worked well in labs failed in messy, real-world environments. Language translation projects produced poor results, showing how difficult human language truly was. At the same time, computers were expensive and slow, and AI programs required far more memory and processing power than technology could provide. Expectations had grown faster than results. In 1969, a famous critique showed major limitations in early neural networks, reducing enthusiasm for connectionist approaches. Funding agencies became skeptical, questioning whether artificial intelligence was delivering practical value. The turning point came in 1973, with the British government's Lighthill Report, which sharply criticized progress in AI research. Funding was cut, many projects were canceled, and the field entered what would later be called the first AI winter. And with that, the first chapter of artificial intelligence came to an abrupt end. The dream didn't disappear. It went quiet, waiting for the technology and ideas that would one day bring it back. In the next part, we'll see how AI rose again, stronger, smarter, and far more surprising than anyone imagined.